In the last video, we discussed how you multiply a matrix by a scalar value, aka if we're going to take an entire array of data, multiply it by a single number, how does that behave? In this video, we'll talk about how do you actually take an entire matrix array and multiply by another matrix, and what are the conditions for which that works. And before we actually get into the how and the why, I think it's important to note that when are we allowed to do it? And we're only allowed to multiply two matrices together if the number of columns in the first matches up with the number of rows in the second. So, like in the first example, it says to take matrix A and multiply by matrix C. And note that in the first matrix we have two columns, in the second matrix we have two rows. So that's an exact match here between A and C. So this would be an allowable matrix product based on that condition. And what it also states is the resulting matrix will have a dimension of m by k. So that's assuming that our first matrix is m by n and our second matrix is n by k. And note that those are both n because it must have the same number of columns as the second matrix has number of rows. And then our answer matrix, what the result of this matrix AC will be, will have a resulting matrix of m by k, which in this matrix we had 2 columns, 3 rows. So the answer matrix will have 3 rows, and the secondary matrix C in this product had 2 rows and 3 columns. It will have basically the answer here will be a 3 by 3 matrix. It will have the same number of rows as A, the same number of columns as C, but the only way to multiply them is since they both had this one had 2 columns, this one had 2 rows. That's the primary condition. And as the packet says, to actually do the matrix multiplication, we're going to have to take the inner product of each row with each column from matrix A and matrix C. Or sometimes it's called a dot product. If you've ever worked on vectors before, it's exactly the same as if we were taking a 2 vector and taking the dot product of that vector with another 2 vector. But let's just do an example because it's kind of hard to. I think it will become more apparent how we actually do it by working through an example. And maybe I'll talk a little bit about, well, why do matrices actually multiply the way that they do? But let's go ahead and multiply matrix A by matrix C. And what I'm going to do is I'm going to rewrite these two matrices out again just so I can show you what I'm thinking of as I'm working on the matrix multiplication. So matrix A is the matrix 2, negative 3, 0, 5, 7, negative 1 half. And matrix C is the matrix 7, negative 3, 0, 0, 1, 5. And these matrices are allowed to multiply because we got 2 rows and 2 columns. And note that it's a very different condition than adding and subtracting. To add and subtract, they had to be exactly the same dimension. To multiply, they don't need to be the same dimension. In fact, they'll only be able to be multiplied if they're the same dimension if they're square. If they're not square, like these two are not, they're rectangular matrices. We're still able to multiply them. And so basically, what it says is that the answer we're going to get is going to have the same number of rows as the first and the same number of columns as the second, which is 3 by 3. So it's actually going to create a larger matrix of data. Why? Well, let's see how we actually multiply it. And to get each element, it's going to be the result of taking the dot product or inner product of the first row with the first column. So basically, I take the first row of the first matrix and multiply it into the second row of the second matrix. And what will happen is the first element in each of those will multiply together, and I'm going to add it to the second element of each of those. So, and this is the same thing as a dot product of two vectors. But what I would get is, well, 2 times 7 is 14. So I'll go ahead and write this math over here in red just so that we can trace. If you need to trace back to how I'm doing this, you can. But I would take 2 times 7 plus negative 3 times 0. And that's just what I'm going to call the inner product, or dot product. I typically refer to it as inner product. But that would, of course, leave us with 14 plus 0, or 14. And that would give us the first element in our new matrix. And note that the first row going into the first column makes the first element in both element row 1, column 1 of the answer matrix. Now moving into the second one, basically now what we do is we kind of go through the entire matrix. We just did the first row into the first column. Well, now we see, well, what about the first row into the second column? And then and do the same exact math. So the inner product of those would be, well, 2 times -3 plus -3 times 1. And again, that would give me, I'll note the math over here just so you can trace back how I'm getting the numbers. That would leave us with -6 minus 3, which is, of course, -9. And this would give me my second element within my answer matrix. And again, since I took the first row into the second column, that's in the first row, second column of the answer. And the new matrix that I get from this from this product has a dimension that matches the full multiplication of it. And if you're wondering, well, why does matrix multiplication work this way? It's a little bit strange, to which I definitely agree with you. If you're wondering that, the simplest explanation is just kind of has to. In order to properly multiply through, we have to do it in this way. And there's a very specific geometric purpose that multiplying provides. And if you look at the example in the book, which describes multiplying this lightning bolt by this particular matrix, in order to properly rotate something, multiplication must work in this way. And it's harder to really get into that without a much more advanced understanding of matrices. So I'm going to not really even try at this point, because we're not really going to get that deep into matrices. But I will post a link to a helpful article which kind of gets into this idea of why it must work the way it does. And this might help you see why matrix multiplication works, for those of you who want to look into this. But if you don't really care that much, what's important is that you actually know how to do it, and the why is a little bit harder to explain, at least in a simple mannerism. Anyways, let's go ahead and finish this product of matrix A times C. But basically now I need to do the inner product of the first row to the third column, and that would give me the first row, third column in my answer matrix. So that would be 2 times 0 plus -3 times 5, which is, of course, 0 minus 15 or -15. And that would give me the third element. And basically, that would notice it's kind of like the distributive property. I'm taking this and distributing into there, into there, into there. And once I've gotten the complete product, that I've now finished with the first row. But I need to do the same process for the second row and the third row, because I kind of have to imagine that I'm mixing all of the elements from the first matrix into the second matrix. And so far, I've only used the first row, so I'm not even close to finishing, right? Because then I need to do, well, what about the second row into each of those, and the third row. So I'm going to speed it up a little bit, but doing the same process. So I would take the inner product of that row into that column, then that column, then that column. And then I'd move along to the third row and do the same thing, inner product, inner product, inner product, working my way all the way through. So from the second row into the first column, that would be 0 times 7, and 5 times 0, that's 0 plus 0 is 0. Then second row, second column would be 0 times -3, and 5 times 1 is 5. So 0 plus 5 is 5. And then I would do 0 times 0, 5 times 5, 0 plus 25, that's 5 times 5 is obviously 25, and that would give me 25. And notice that in this, from the second row, since the first element was 0, what happened was it really just didn't do anything to the first row, because right in each of those inner products, 0 was multiplied into those, so those did nothing. But what happened with the second one is it multiplied them each by 5, which just took that row and multiplied by 5, and that's kind of the end result I get. So notice that a 0 within a multiplication will kind of be a skip for a row. And if you're trying to scale up, say particularly just the y-axis, instead of multiplying a scalar by just 5, you could multiply it by like 0.5 or 0.2, and that would multiply just, say, for example, the y values by 5 instead of the x values. And you could use these specialized special matrices to scale. Say I was going to take that lightning bolt and stretch it just one way or shrink it. You wouldn't want to it wouldn't want to be scalar multiplication. You'd want to use matrix multiplication. And also you could use a particular matrix multiplier to actually rotate it about any degree axis instead of just stretching and shrinking. And you could do just about whatever you want to an image if you know how, and which matrix to use. Anyways, let's move on to the last row. So taking the third row, now I need to do that into each column. So 7 times 7 is 49, and 1/2 times 0 is 0. Then I would do 7 times minus 3 is negative 21, but I also need to subtract 1/2 times 1, which is minus 1/2, so that would be minus 21.5. And last but not least, 7 times 0 is 0, and negative 1/2 times 5 is negative 5/2, which is negative 2.5. And I'm just going to use decimals just because. But long story short, what I would get is a 3x3 matrix, and that would be the result of the product of those two matrices. In the next video, I'll do a couple more examples, and we'll discuss more about how to do matrix multiplication and some further properties.